This is question number 48 from chapter 23. It reads, a negative 5.5 diopter lens is held 14 centimeters from an object 4 millimeters high. What is the position, type, and height of the image? So I've made a quick sketch. Immediately you should recognize that since this is a negative sign by sign convention, this is a diverging lens. And I've written my equations here in green. Immediately I should be able to use the power equation to solve for the focal length. Now, this isn't absolutely required, but let's go ahead and do it. I find I usually start solving my problems this way. I'll explain in just a bit why you don't have to do this, but I'm going to solve for the focal length, and the focal length is going to be 1 over the power in diopters. Now this is going to be negative, so it's going to be 1 over negative 5.5 diopters, and I get a focal length of 0.1818 meters, or about 18.2 centimeters. So we know that this is about 18 centimeters, and the distance to the object is 14 centimeters. So I know relatively where I'm going to be drawing it. It's right here inside the focal length. Now, because this is a diverging lens, the location of the object isn't super critical, as it is for a converging lens, which changes radically as soon as you cross over that focal line. So this is the reason why I usually like to know what the focal length is in meters, especially if I know what the distance to the object is. I'm going to go ahead and complete the ray diagram. It doesn't ask me to do that, but I think it's good practice to know these things. If I come here, I'm going to refract in a line that's related to this focal line here. I'm not going to draw it in all the way. Well, let's go ahead and do that. I guess I do need that guideline. Looks pretty decent to me. And the second line would be the ray that would pass through this focal point here on that side. I'm going to go ahead and draw that construction line in here. Looks like I got an extra line in there that I'm going to get rid of. Oops. Okay, and then the last one is the ray that passes through this guy on the way to the lens, and it just passes right through. Oh, I guess I never finished this one. The one that would have passed through the focal length will refract parallel to the principal axis, and then this guy just busts on through. So now I have these diverging rays. They appear to originate on the same side of the lens as the object is. So if I follow those lines back, here's this one. There's the middle one. So that's ray 1, ray 2, ray 3. So ray 2 comes straight back. Ray 3 comes straight back, and so now my image is formed here on the same side of the lens. We can see that the image is smaller, it's virtual. The distance to this image here should be negative because it's virtual. So I have a lot of information ready to go that should be consistent with my calculations as I go ahead and move forward. From a quantification side, when I look at the fact that I have the focal length and I'm being asked to find the height of the image. So, hey, I have the height of the object. It's 4 millimeters. If I knew the magnification, then I could easily find the height of the image. I only have the distance to the object. I don't have the distance to the image here. And so it's clear now that I'm going to have to use this equation, the thin lens equation, to find the distance to the image, and then I'll be able to figure out the magnification and the height of the image. So I'm going to go ahead and start with that. It's going to be 1 over the focal length is equal to 1 over DO, distance to the object, plus 1 over DI. Remember that my focal length is negative, so I'm going to now solve for distance to the image by subtracting 1 over DO from both sides. I get 1 over F minus 1 over DO is equal to 1 over D sub I. Now I'm ready to plug some numbers in. The focal length is 0.182, let's call it, so it's 1 over negative 0.182 meters. Again, that negative sign is because the focal length is negative for this type of a diverging lens. It looks like I left it off here. This negative sign, of course, carries over. And then from that, I'm going to subtract the distance to the object. So I'm going to subtract 1 over the distance to the object, which in this case is 14 centimeters or 0.14 meters once I make that conversion. And that's going to be equal to 1 over the distance of the image. Basically, I have a negative fraction, and I'm adding to it another negative fraction, so the distance of the image should be negative, which is what we talked about earlier. This is negative by sign convention. So solving for the distance to the image, negative 7.9 centimeters. Now I, of course, could convert that to meters, and I would get negative 0.079 meters is equal to the distance to the image. Now that I have this information, I'm ready to use the magnification equation. I actually don't even need to know the magnification. I'm going to use these two terms right here because I have the distance to the image, the distance to the object, the height of the object, and I'm looking for height of the image. So my last step will be to basically do that. I'll do that work over here, starting in this portion of the page. I'll say that the height of the image over the height of the object is equal to negative di over do. Solving for the height of the image, it's going to be that ratio, negative di over do times the height of the object. Plugging in my numbers, I'm now going to get for di negative 0.079, so that double negative creates a positive here in the numerator, meters, divided by the distance to the object, which was 0.14 meters. And I'm going to multiply that by the height of the object, which is 4 millimeters, or 0.004 meters. And when I run that through my calculator, my final answer for the height of the image is going to be 0.0023 meters. Or I can say that that height of the image is 2.3 millimeters. Again, why I recommend kind of knowing the ray diagrams is because this smaller height of the image is consistent with what we expect from this type of a lens. Also recognize that this is a positive number, which means that this is an upright image here. Again, everything double checking.